Hello, everybody. Well, this is quite a situation for all of us to deal with, and I hope that you and your loved ones have at least not been directly affected by the COVID-19. Although our lives have all been affected to a significant extent. So hopefully, all of us are able to just keep moving forward in some sense, just like what I'm trying to do right now. Trying to keep my courses and other activities going. Although of course there have to be a lot of changes and not just transitioning to online. So to focus on what's happening in, in this class, I've mentioned uh, certain changes in email, but I want to just run through everything. Certainly those things that affect you the most. As far as grading is concerned, so um, I've removed the group project. I have removed test three. So there's only WebAssign homework, um, two tests, and a final. And you test one, and the other two tests will be given in WebAssign, unproctored. Um, and then, well, actually, that's it. So just two tests, final, and homework. So the WebAssign homework is 15%. Um, test one and test two are 15% each. The final is 25%. That adds up to only 70%. So what I will do for remaining 30% is I will look at your WebAssign average, your test one score, test two score, and final. After using your final to replace your lowest test, if it will help. So after you take a final, if a final is your lowest, then I won't do any replacement of test scores. But if your final is higher than test one or test two, I will replace the lowest of a final. So after that, I'm sorry if this is confusing, but um, after any replacement of lowest test scores has been done, I will look at your um, homework average, test one, test two, final, take the highest one of those, and I'll put that in the remaining 30% of your grade. Um, so, so in other words, if you do particularly well on the final, it would count for quite a lot. So whatever you do your best on is going to help you significantly. Your highest item will count for um, at least 45% of your grade. Um, okay, another adjustment. I don't know if I announced this in email. So so what will happen is with WebAssign homeworks, I think I had it previously set in the WebAssign gradebook to drop the lowest homework grade. I will now be dropping the lowest four homeworks. So that's 2 weeks worth of homework that if it doesn't get done, don't worry about it. It'll just get dropped. Another thing about homework is um, that after a homework due date passes, you are still able to turn it in up to 2 weeks late. That's the maximum WebAssign would allow. I tried. I wanted to have no late submit. I wanted to have totally free form where you could turn it in anytime you want, but WebAssign wouldn't let me give an extension longer than 14 days. But you have uh, uh, up to 2 weeks after that to still turn it in. But WebAssign will accept it, and there is no late penalty. Now, had the routine of homeworks being due on Mondays and Thursdays. I'm sticking with that routine. So the homework from the last section that I covered before the break, which was variation of parameters, that shows in WebAssign is still being due tonight. But again, if you haven't had a chance, and I certainly understand if you've not, do not worry about it. You automatically have 2 extra weeks. Um, the section I'm going to cover today, which corresponds to 5.1 in the text, that's the last material for test two. Um, So the way tests are going to work is on so a week from today, Monday, April 6th, I'm going to post test 2 in WebAssign. And um, it'll just sit your WebAssign, and you have until the night, 11:59 p.m. on Wednesday. So you have 3 full days: Monday, Tuesday, Wednesday. Um, Anytime during that 3-day period, you can get it done. Um, and I originally set it for 75 minutes, um, and has 2 attempts. I'm going to double that. So that way it's 75 minutes per attempt. So whereas with homework you get 5 attempts, test you get 2. So I'll just the time limit to correspond to that. So 150 minutes total for test 2. Um, for there's a practice test that's already on WebAssign. So there's an untimed one that you can take up to 100 times. There's 100 attempts allowed. Um, and then there are some timed ones. I believe there are 5 of them that have the time limit, so you can practice that way. The actual test 2 will have problems of the exact same nature as as on the practice test. The first problem, the functions are changed, but the formula that you use is the same. It's a reduction of order problem. Um, for the other problems, they are completely identical except for changes in numbers. Also, for the practice test on the course website, just as you went there to get the practice test 1, I posted a full solution to practice test 2, so you can see how to work out those problems. So be sure to take advantage of that. This is a crazy time. There's a lot for us to deal with. We can all imagine the stress that we must under just from experiencing ourselves, but we're also many sources of stress for ourselves and each other. For, for others that we cannot imagine. So I urge you, if you're having trouble keeping up because of your own situation, it's very important that you contact me. It's already more difficult in this online format. Instead of seeing, some of you in LAB 102 every Monday, Wednesday when I give class, now I'm just here in my office and I don't see anybody. So um, I I will do virtual office hours if you need to come see me. So virtually. Again, please contact me. I will understand. I will do what I can. Um, but it's very important that you do that. Um, so uh, we are all struggling, um, but it's important um, uh, that we also try to help each other through it too. Uh, and the more aware we are of what's going on, the easier that'll be. Um, okay, so um, in Canvas, Canvas is where you should check your grades. Now, it will not be updated in real time from WebAssign, but what I will do is, I did it just before class now, this each week I will go through Canvas and update to account for WebAssign averages, because homework grades are not automatically synchronized from assigned to Canvas. Um, and make sure your grade is up to date there. I went through to account for the fact that assignments are dropped, so everybody's homework average went up just now, unless it was already at 100. There is a statement of academic honesty that I announced on Canvas. Many of you have gone ahead and signed that. It's very important that everyone take care of that. There's still a number of you who have not, um, and that needs to be done before the second test. So I expect you to live up to what is in that statement. Please sign that before test 2. So this is what will give you the 30% of a grade that's set to the highest of one of your averages. So once you sign that, I will update that in Canvas. And if I take a look at this now, it looks like the majority of you have, but there roughly 1/3 of you, a little more than 1/3 of you, still have not. So um, please take care of that sooner rather than later. So what I will do is I will record lectures roughly around class time, just so I can keep my own routine, and then post them shortly after. So so as early as every Monday, Wednesday afternoon, you should be able to see the class posted in the usual place in the course website. So I want to try to keep things as much the same as possible, aside from accommodations on grades. But as far as the way things work, I want to try to keep that the same as much as possible, just for the sake of continuity. So, so if you have any questions or concerns, again, I urge you, please let me know, and I will do what I can to take care of it. Okay, so now, for the first time in more than 2 weeks, it's time to actually get back to covering some math. I realize that it probably is the furthest thing from your mind, and it honestly feels weird to be teaching again, since it feels like forever since I was, even though it's only been a little more than 2 weeks. But I'm also hoping that by trying in some form to keeping our activities going, and keep continuing to work towards towards our futures, that that I can actually also in some way be helpful to us. Okay, so without further ado, so this corresponds to section 5.1. Linear models, we've seen them for first order problems, that was some time ago, like those mixing problems, etc. But now we're looking at applications for second order linear equations. So this corresponds to section 5.1 in the textbook or ebook. In my notes, it's section 3.7. Okay. So what we're going to look at is just one application. So there'll be one problem of this kind in the test, and one homework set, 5.1, that is due this Thursday, April 2nd. Okay, so we're modeling a spring. So we have a badly drawn spring, and we have some object attached to the spring. So what will happen is, for instance, if you pull down on the object and then let go, then there's going to be some vibration. So the length of the string is going to oscillate over time. So if I let my solution u of t be the displacement of the string. So when u equals 0, so that is the equilibrium position. So if I just attach this to the spring and just let it sit there, that would correspond to u equals 0. The downward direction is positive u. That's very important that we keep in mind the orientation. Positive is this direction, and the negative displacement is going up. So the way that we can model the motion of the object on the spring is using Newton's second law. So force is equal to mass times acceleration. So if we apply that here, we have the following. Mass, m, times acceleration. Well, acceleration is the second derivative. U is the displacement, so the acceleration would be u double prime. Okay. So that is equal to the sum of all the forces acting on the object. So we have m times g, gravity, so it would be mass times the acceleration due to gravity constant. We would also have Fs, this is the spring force. Fd is a damping force. I'll write all this down. And then this F with no subscript is external force. So here we have spring force. And that is equal to minus K. K is the spring constant. That'll be very important in these equations. Okay. And then L is equal to elongation. So if I just attach the spring, attach the object to the spring, and what will happen is that will extend the spring to a certain extent past the equilibrium position. So so whatever gravity does to extend the spring, that is L. Now, K and L must satisfy this equation. So we have K times L is equal to mg, the force due to gravity. So the idea is however much the object has stretched the spring when it's at the equilibrium position. So if we're at equilibrium now, that would be the length L. We can use that information to solve for the spring constant K. So in some problems, the spring constant may be given. In other cases, you need to solve for it using information that's given about the object, like its weight or its mass, and also information about L, how much it is stretched the spring. So that's the spring force that goes for here. And because KL equals mg, the minus KL part is going to cancel with the mg term in here. So that's the spring force. This is the damping force. And that's equal to minus some constant gamma times u prime. So the damping force is always proportional to the velocity and acting in the opposite direction, because what does damping do? That reduces motion. So that's going to reduce the acceleration. So so to cause the amplitude of vibration to decrease over time. So the first problems we'll consider will have no damping, but at some point we will work it in. And then finally, this capital F out here with no subscripts, that is any external force that might be applied to the object that would affect its motion. Initially, we'll assume there are no external forces, but at the very end, we'll include that effect also. So we have these three things: spring force, damping force, and external force. The last two being, I guess you could say, optional to describe the motion of the object over time. So if we put all of these things together, then we have a second order differential equation. Now, you can look here at the board. Fortunately, it is on video, so you can go ahead and pause this. So make sure you have all of this and pause it and get all of it. I'll still give you a warning when I'm about to erase everything, because it's not like in the classroom in LIB where I finish one board and then I move to the other board, and you can still take notes from the first half of a board. So get ready, I'm about to erase. Okay, so here's our differential equations that we will be solving. mu double prime plus gamma u prime plus ku is equal to capital F. So the mass, the damping constant, and the spring constant K become a coefficients, constant coefficients of this equation, and then we have whatever function, so let's capital F t. It could be any given function of t. So, and then we have u of 0, initial condition, the initial position, and then u prime of 0, is the initial velocity. All right. Now, some terminology that can come up in problems. So let's suppose that it's stated that that the object is sorry, I want to make sure that I have everything here. So, so the position is equal to 0 if it's stated in a problem that it's equal, that it's initially as the object is initially at its equilibrium position. So u of 0 would equal 0 in that case. Whereas if it is stated that the object is pulled down or even pushed up, so have a non-zero initial position, but let's just say I pull down the object and then I just release it. That would mean u prime of 0, the initial velocity, is equal to 0. As opposed to actually, like suppose the object is at equilibrium, so u of 0 equals 0, and then I impose a velocity on the object from an equilibrium position. Then u prime of 0 would be non-zero. But if a problem states that it is moved to a certain position and, quote, released, that's u prime of 0 equals 0. So that's how to translate the wording of a problem into initial condition. All right. Now, this kind of differential equation, you already know how to solve it. It's just now it's put in context of an application. Because you would solve this the same way that you would solve the problems from the last several sections. You would take the characteristic equation, which would be that would be m r squared plus gamma r plus k is equal to 0, and you would find the roots. And that would give you the homogeneous solution. And then if there is an external force that's non-zero, then you would have to use one of the methods from the last couple sections, like undetermined coefficients or variation of parameters, to find a particular solution and put all of that together. So what have you been doing in the last couple sections? you're just going to keep doing that. It's just that there may be a little additional work up front to take the verbal description of a problem and obtain the differential equation from that. Okay, so before I get to some examples, I'm going to talk about a few different scenarios that all give different behavior of the solution. So the first scenario is we assume that there is no damping, so gamma is equal to 0, and there's no external force either, so capital F of t is 0. So in that case, we have this equation, mu double prime plus ku is equal to 0. So our characteristic equation reduces to mr squared plus k is equal to 0. Now keep in mind, m and k are both positive constants. So now we have m squared is equal to r squared is equal to minus k over m. So r is going to be purely imaginary. It's going to be plus or minus omega naught times I, where omega naught is equal to the square root of k over m. Now, omega naught has a name. It is called the natural frequency. Okay. So that is the frequency at which the object is going to oscillate after whatever initial conditions are applied. So, because we have complex roots, in fact, they're purely imaginary, so our solution is going to consist of a sine and a cosine term. So the general solution also, terminology from the homework in WebAssign, the solution is referred to as the equation of motion. So a problem will say, find the equation of motion. All it's asking you to do is come up with a solution of a differential equation. So it has this form, u of t is equal to a constant times cosine omega naught t plus b sine omega naught t. So this number omega naught is very important. It drives the frequency at which the object is going to oscillate, and it's going to oscillate forever because sine and cosine, they oscillate between plus and minus 1 forever, so obviously physically it's not very realistic, but in a real setting there would be some damping, but we're just neglecting that effect here. So if there was a damping force that was extremely small, then yes, the object would appear to be oscillating forever. It would take a very long time for it to return to rest. Okay. Now, some things that are that can be inferred from the solution that help describe the motion of the object. Okay, so I'll just give you formulas for these. So the amplitude, you may recall years ago, like trigonometry class, graphing sine and cosine curves, you had to figure out the period, amplitude, phase shift. So the amplitude, which I'll call r, that is the square root of a squared plus b squared. So in fact, this allows you to write u of t in its alternate form, r cosine omega naught t minus delta. And this comes from the trigonometric identity for cosine of a difference of angles applied to this, where tangent of delta is equal to b over a, and that is called the phase, also known as the phase angle. So this shows that the object will oscillate between plus and minus r forever. So that's like the height of a wave above equilibrium. Finally, this is something that the homework may ask for. The period of the oscillation is 2 pi divided by omega naught. So I'm going to put a box around this and around this too. So these are things that certainly the homework will ask for as part of the final answer. Sorry, one thing I'm going to look at real quick is, let's see. Oh, in WebAssign, I just want to make sure nothing is getting overlooked. Look at the homework for this section. Okay, yeah, because certain problems will ask for the period, equation of motion. Okay, yes, it does ask for the amplitude in at least one problem. Okay, most of the time it's just asking for the equation of motion. Okay, so if you go ahead and find the equation of motion, then the amplitude, so I'll put a box around this too. Okay, so these are the three things: the equation of motion, amplitude. I'll extend my box to cover this. So here's your general solution. You find the A and B based on the initial conditions. Once you have the A and B, that gives you the amplitude if asked for. And from your characteristic equation, your natural frequency, that can be used to give you the period. So these are the things that will be asked for. Now, all this from a no damping case, but I'm also going to look at cases of damping and also external force. Okay, so what you can do if you see that there's no external force and there's no damping, what you can do is first just jump directly to here. Get the natural frequency. So square root of k over m, bam. That's your omega naught. That no need to go for a characteristic equation. We know how it's going to turn out. It's always going to be this. Then from there, you go directly to here and have your general solution. Figure out the A and B from the initial conditions. And then you have your equation of motion. And then if it asks for these items, only some problems do, then you know how to get them also. I mentioned, say period, there's a third item before the amplitude because it almost rarely asks for the amplitude. Also, you can figure out the period without getting the equation of motion. All you need is the spring constant and the mass to get your natural frequency, and then you have your period. Okay, so here's how we can describe the motion of the object on the spring when there's no damping, no external force. Then we have this endless oscillation at this frequency, this amplitude, and therefore this period. So be sure to get all that, and I'm about to erase. Okay. The second scenario is when the constant coefficient of a first derivative, gamma, is non-zero. So now we have damping. So the characteristic equation is mr squared plus gamma r plus k is equal to 0. So now I have this term of gamma r in there. And the roots will now be minus gamma over 2m. So we do have a real part in there now. Plus or minus square root of gamma squared minus 4km all over 2m. So this other part here, depending on the values of gamma, k, and m, could be real or imaginary, or it could be 0. So we actually have to consider all three possibilities. All right. So first scenario is where a discriminant gamma squared minus 4km is positive. So then we have real roots. Okay. So what happens in this case is when you have real roots, and they're going to be distinct real roots because this part will be non-zero. So you have minus gamma over 2m plus or minus whatever this is. That's when your solution has exponentials. So we have a constant e to the r1t plus another constant e to the r2t. And the other thing is, because here we have minus and then gamma over 2m, that's the absolute value. And here we have this number here, square root of gamma squared minus 4km. That's going to be smaller than gamma over 2m. Because look this way, if this wasn't here, the minus 4km, we just take a square root of this and just get gamma. We'd have gamma over 2m again. But something is being subtracted off. Something small because this is still positive. So in other words, this is going to be smaller in magnitude than this. So the roots are both going to be negative in this case. So because the roots are both negative, these are both decaying exponentials. So this goes to 0 as t goes to infinity. Not only that, because they're decaying exponentials, there's no sine or cosine here, then what happens is you don't see any oscillation whatsoever. So this becomes from a relatively large value of gamma compared to k and m, that there's so much damping force that, say, like you pull down the object and release it, and it just doesn't even bounce at all. It just basically returns to rest fairly quickly. So that's when there's a relatively large damping force. The second scenario to look at is gamma squared minus 4km is negative. And what happens in that case is you get complex roots. So u of t is equal to a constant. And then we have an exponential minus gamma over 2mt. So this minus gamma over 2m, that's the real part. And then you have cosine mu t plus b, same exponential, minus gamma over 2m times t sine mu t. Now, what is mu? The frequency in this case is square root of 4km minus gamma squared, square root of that, all over 2m. Okay. And this is called quasi-frequency. Okay. And also capital T, which is 2 pi over mu, is a quasi-period. Now, remember from an undamped case, square root of k over m, the omega naught, that was called the natural frequency. Now, what happens here is, let's suppose gamma goes to 0. If gamma was 0 in this, then this whole expression, you could try working out yourself, it algebraically simplified to omega naught. It would simplify to square root of k over m. So this is for a case where there's not much damping force. It's small compared to k and m, resulting in this quantity up here being negative. So what happens is the amplitude changes over time. R is equal to this exponential minus gamma over 2mt times the same amplitude as in the undamped case, square root of a squared plus b squared, where a and b are the constants here. Those constants, again, depend on the initial condition. So we have the amplitude that we start off with for the undamped case when t is 0, but as t increases, the amplitude is decaying to 0 because you, say, pull down the object, you release it, and it's going to oscillate, but less and less, eventually settling down to the equilibrium position. When there's damping, instead of the natural frequency of omega naught equals square root of k over m, you have this quasi-frequency that indicates the frequency of the oscillations and also essentially the period. It's not a uniform period because period suggests that it's oscillating coming back to the same spot after that period, but it's not because the amplitude is decreasing. But one full cycle of at least the oscillatory part, setting aside the exponentially decaying part, would have this period of 2 pi over mu instead of 2 pi over omega naught. So mu is playing the role of the frequency in this damped case. All right, and there's one more scenario. I've talked about gamma squared minus 4km positive and negative. So particularly interesting cases when gamma squared minus 4km is equal to 0. So the roots, both of them, are equal to minus gamma over 2m. So the equation of motion is different in this case. We have a constant, e to the r1t, plus another constant, t, e to the r1t. So that we have a factor of t here that that influences the motion. It's still going to be decaying to 0 via displacement because we have a negative exponentials in both cases, negative exponents in both cases. So we still have exponential decay, but it's going to be because this part is increasing over time. That will not stop being exponential decay, but it will offset it to a certain degree. So it's not going to go to 0 quite as quickly. So here we have little little damping force, moderate damping force, large damping force, and how it affects the motion of the object. Okay. So now what I want to do is a couple of examples. I have one that is undamped and one that is damped. And then after that, we'll take a look at the case where there's an external force. So I'm about to erase. Okay, QuickTime crashed. Actually, it's a rather convenient time to do it, I guess. Okay, so I'm about to do an example. All right, so we have the object. We're given a weight of 2 pounds. And so you can call this W for the weight. It is not the mass. It is the weight, W. And it stretches the spring by a length of L, which is given to be 6 inches, or we'll work in feet. So, so half a foot. And it is pulled down 3 inches, or 1/4 of a foot. So this is going to be U of 0. So that's one of our initial conditions. And then it is released. So that tells us the other initial condition, U prime of 0 equals 0. We did not impose initial velocity on the object, only initial position. So let it go. Okay. Now, other information, no damping. So gamma equals 0. Case. So what is asked for is the equation of motion. So the sort of thing that the homework will usually ask for. It's asking for the solution, U of t. So what we have is U of t, the general solution is going to be A cosine omega naught t plus B sine omega naught t. So we can conclude this right away due to the fact that there is no damping. So that lets us jump to that right away. But now we always have particulars. A and B come from initial conditions, and the very important number omega naught comes from the spring constant K and mass M. So omega naught is equal to square root of K over M. But right now, at this moment, we have neither K nor M. But we do have enough information to get those things. So what we have is the force due to gravity, mass times the gravity constant, is equal to the weight of the object, which is equal to 2 pounds. So therefore, the mass, let's rearrange this. We get weight divided by g, so that's going to be 2 pounds over 32 feet per second squared, the gravity constant for English units, and we get 1/16. So we have a mass, and that is 1/16. As for the spring constant, K times L is equal to mg. Well, now we have enough information to solve for, so mg is equal to 2, and then the length, when we attach the object to the spring, it stretches it to a length of 6 inches. So that's 1/2. So therefore, k is equal to 4, and m is equal to 1/16. So now our omega naughts square root of equals the square root of k over m is 4 divided by 1/16. So it's the square root of 64, which is 8. All right, so now we're able to describe our general solution. So it's a cosine 8t plus b sine 8t. So that is the general solution. But now we have to find a and b based on the initial conditions. So we need u prime of t, so that's going to be minus 8a sine 8t, 8b cosine 8t. So now we have u of t and u prime of t. We plug in t equals 0 in both. So u of 0 is just going to give us a, and that has to, and then u prime of 0, we plug t equals 0 in here, and that's going to be 8b 0 because the object was just released, not given initial. So there's no sine term after all. So the equation of motion, so our final answer is u of t is equal to 1/4 cosine here. So 1/4 cosine 8t. So the problem's asking for the equation of motion. That would be your final answer right there. And what we can conclude is amplitude r is equal to square root of a squared plus b squared, but we only have so it's just 1/4. And then the period is capital T equals 2 pi over omega naught, which is 8. So the period is going to be pi over 4. So if those things are asked for, the problem, this is how you get them. So square root of a squared plus b squared, where a and b are constants in front of cosine and sine. Period is always 2 pi over the natural frequency omega naught. So in this case, it's going to be pi over 4. So it has a fairly short period, so somewhat rapid oscillation, but not much of an amplitude. So what happens in this case is it's just it's pulled down to by 3 inches. It's going to oscillate between plus and minus 3 inches forever because there's no damping. All right, so that's an example for the undamped case. So get your K and M. Depending on the units of the information you're given, you may need to solve for M, and then you can use that to solve for. On the other hand, if you are given, if you're given the mass of the object, then you need to then you can just use that in the formula for omega naught directly. Now, another thing that can happen is here I have KL equal to mg. This is the force due to gravity. In some cases, a problem might simply say so if I label this in this case due to gravity, but the problem may say that a force of say a certain number of newtons, for example, an amount of force stretches the spring length. So in that case, if you're given not a force due to gravity, but just some other force happens to stretch the spring a certain length, L, so you're given L, then you can use that to solve for K. So K is going to be whatever force is applied to the object, often gravity, divided by L, the length that the spring is at as a result of that force. So if it's gravity, you attach the object to the spring, it just hangs there, it stretches the spring a certain length. That would be the L in that case. Or some other force, like an external force is applied to the object, and you're given to stretch the spring a certain length, so again, it's force divided by length. That is the value of K. All right. So if you're given the weight, don't forget to divide by G to get the mass. There are possibilities that you might be given the mass. So get your K and M using whatever information that you're given. And then you have your natural frequency in the undamped case that leads directly to your general solution. Using initial conditions, like is the object pulled down or pushed up? Is it simply released? Or is it given initial velocity? Or is it starting from rest, in which case u is 0 equals 0? So based on what the initial conditions are saying, that's how you translate it into values of u 0, u prime is 0. That gives you the A and B. Then you can complete the equation of motion from initial conditions. A and B give you the amplitude, and then omega naught, 2 pi over omega naught gives you the period. Right. So that's my undamped example, and I'm going to erase and then do a damped example. Sorry, before I continue, I just want to take a quick peek at the fast forward until I return to the board. Okay. Okay. Okay, I'm looking at the problems. Like in many cases, they give you the weight in pounds, so you do what I just did in the example to get the. In one case, you're given M in kilograms, but you're also given the spring constant. And in one case, you're given the object has a mass of 1 slug, so in that case. Okay, so make sure all the bases are covered so that you're ready for the homework. So now, a second example that includes damping. So the weight is given to be 16 pounds. L is equal to 3 inches. or 1/4 of a foot. Then the damping constant is given to be 2 pound-second per foot as the unit for the damping constant. Okay. Now the so the mass is given to be at equilibrium initially. So the u of 0 equals 0 with a downward velocity of 3 inches per second. So u prime of 0 is equal to 1/4. So remember, anything with inches converted to feet. And keep in mind, very important, downward is positive. That's why u prime of 0 is given a positive value. If it had been pushed up, then it would be negative. Okay. Again, we want to know what is the equation of motion. Okay, so we need our constants. So m is equal to the weight divided by gravity, so that's going to be 16 pounds divided by the gravity constant of 32 feet per second. So the mass is equal to 1/2. Okay, gamma is 2, and then K is equal to mg over L. So remember, force divided by length. Well, in this case, force due to gravity, so it's weight divided by length. So that's going to be 16 divided by the length that it's stretched to is 1/4, so it's going to be 64. So we have K, we have M, and we have gamma. So now our differential equation. So it's m u double prime plus gamma u prime so that's our differential equation, the general form when there is damping. Now fill in all the constants that you have. So we have 1/2 for mass, 2 for damping, and then 64 for the spring constant. So the roots of our characteristic equation are now the formula from before, minus gamma over 2m plus or minus square root of gamma squared minus 4km all over 2m. So when it gets filled in, the numbers are not very nice in this case. So minus 2, plus or minus 2 times the square root of 31i. So what happens here is 4km turns out to be 128. So we have 4 minus 128. So we have square root of minus 124 up top. And we simplify as much as we can to get these complex roots. So, so our general solution, so it's a constant, I'll call C1, e to the minus gamma over 2mt cosine. Now, this right here is the that's the mu part. So the imaginary part that goes into sine or cosine, is the mu, the quasi-frequency. So ut plus C2 e to the minus gamma over 2m t sine ut. But the idea is the exponentials, the minus gamma over 2m, that's the real part of your roots. And the imaginary part goes to the sine and cosine. So I have C1 e to the minus 2t cosine 2 squared of 31t plus C2 e to the minus 2t sine 2 squared of 31t. Okay. So now all that's left is to solve for C1 and C2 using the initial conditions. So if I plug in t equals 0 in here, well, sine of 0 is 0, cosine of 0 is 1, and e to the 0 is 1. So if I go here, u of 0 is just C1. So that always happens in these cases of complex roots. But u of 0 is 0 because the mass starts at equilibrium. So C1 is 0. So the first term of our solution is just gone. U prime of 0, we take it into account. So now we know this term is 0, so we can forget about it. So u prime of t, rather, will be the derivative of this term. Now, unfortunately, that requires a product rule. So that's going to be minus 2c2 e to the minus 2t sine 2 squared of 31t, and then plus c2 e to the minus 2t cosine 2 squared of 31t times 2 squared of 31. By chain rule applied to derivative of sine. If I plug in t equals 0, u prime of 0, well, that term will go away. Cosine of 0 is 1, e to the 0 is 1. So what's left is c2 2 squared of 31 and that has to be equal to u prime of 0, which is 1/4. So that lets us solve for C2. So that's 1 over 8 square root of 31. So now we can write down the final equation of motion. So that's C2, 1 over 8 square root of 31, e to the minus 2t, sine 2 square root of 31 t. All right. So that describes the motion of the when it is given a downward velocity from its equilibrium position. So whenever it happens, you're going to assign, in that case, when you have complex roots. Okay. Quasi-frequency. That's mu, that's 2 square root of 31. And the quasi-period, t is 2 pi over mu. And that's going to be pi over square root of 31. Okay. All right, so that's an example involving damping. Okay. Now, let's see how we're doing as far as time goes. Yeah, it was taking quite a bit of time already. On page 86 of the notes, I have a third example all worked out that's similar to this one, also involving damping. It's kind of a combination of a previous two examples. So there is damping, and in that problem, you're given the mass of 20 grams. So that is your m, and then you have to multiply that by the gravity constant to get the weight for this equation here. Also, it is pulled down 2 centimeters and released. So in that case, u of 0 would be 0.02 meters, and then u prime of 0 would be 0 because it's pulled down and then just released. Okay. So I'll refer you to page 86 of the notes where you can see that example completely worked out as I've done here. Remember to convert your units. If you're given inches, convert to feet. If you're given centimeters, should convert to meters, and so on. Okay. All right. So now I'll cover one more case that deals with whether it actually is an external force. So about to erase. Okay, so the last thing I want to talk about is force vibration. So it's mu double prime plus gamma u prime plus ku equals capital F of t. That is non-zero. So we actually have some external force being applied. Now, you know how to non-zero right-hand side, you use the method of undetermined coefficients or a method of variation of parameters to solve a problem. But what I'm going to do here is I'm just going to focus on a particular case. So I'm going to let capital F t be equal to some constant, which I'll call F naught, times cosine omega t. So there's this oscillatory force being applied to the object over time. So F0 is the amplitude and omega is the frequency of that external force. And I'm going to assume no damping, so gamma is equal to 0. So the equation of motion, u of t, is going to be the homogeneous solution plus a particular solution. Now, in a case where there is no damping, then we know what the homogeneous solution looks like. So it's going to be a cosine omega naught t plus b sine omega naught t. So that's this part right here. And then this part, what form does the particular solution have? Well, it depends on how omega and omega naught relate to one another. Now, recall omega naught is square root of k over m. But omega can be anything. But whether omega equals omega naught affects the form of a particular solution. So I'm going to handle two different cases here. So in a case where omega and omega naught are not equal, I'm going to have, I need to pick what I want for my constants. Okay. Actually, I want to match terminology that I've given previously with undetermined coefficients. So C1 and C2. And we're going to have A naught cosine omega t plus B naught sine omega t. And that's only in the case where omega and omega naught are not equal. If they are equal, then these terms would have the same form. They'd be redundant. So what happens in that case is you have A naught t cosine omega t plus B naught t sine omega t. That's where omega equals omega naught. So when there's agreement between the frequency of your right-hand side and the frequency of your homogeneous solution, that's where you have that t to the s factor that you've seen from undetermined coefficients, and s would be equal to 1 in this case, and that explains the factor of t. Okay. Now, so what ends up happening is, I'll just cut to the chase here. Omega is not equal to omega naught. And then what I would do is I would take this form of a particular solution and substitute it into the equation. Keep in mind that gamma is 0. And you work out the second derivative and match all that to this f of t right here. So method of undetermined coefficients that you have been using previously. So what would happen? What does a particular solution look like? Particular solution is f naught over m omega naught squared minus omega squared cosine it should be 1. Sorry, no minus there. Clicked the wrong line. Alright, so that particular solution has this form. Now, and remember, omega is not equal to omega naught, so we're not going to have divided by 0 down here. But if omega is close to omega naught, this number is small, therefore the whole fraction is large. That means that the amplitude of these forced vibrations is going to be large. Okay. Now, all right. Now, in the case where omega equals omega naught, then the particular solution is going to be f naught over 2m omega naught times t sine omega naught t. Okay. Now, if you now think about it, like let's suppose that okay. Now I was thinking about how you could arrive at this formula from this one, possibly using L'Hopital's rule, but actually L'Hopital's rule would not apply in this situation. But what I want to case is very different from this case to this case. Why? Because we have oscillation in both. We have F naught in both. But here we have this factor of t here. So what does that mean? That means that over time, the amplitude is increasing. Well, in the case where omega is not equal to omega naught, we have a natural oscillation frequency of the mass in the spring without any external force. The external force is affecting the equation of motion, but it's doing so at a different frequency. So what ends up happening in this case is there's still oscillation happening at the frequency of a force, and then there's also the homogeneous solution, unless the object is starting from rest, then you wouldn't have this here. But the point is, you would still have oscillations of these two separate frequencies, and there's a limit on how much oscillation you can have in that case, from considering this term, and this term. Equal to omega naught. When omega equals omega naught, then those frequencies line up and you get this kind of a resonance effect, causing an increase in amplitude over time. So you have a force of a limited amplitude from just the object itself, oscillating a spring without any interference, and then you have the external force also of a limited amplitude. But when the two act in concert, then you get unlimited oscillation that's going to increase over time. So it's going to start oscillating and then oscillate over a wider range because of that coinciding of those frequencies. So it's a very interesting effect that happens by obtaining the particular solution. And in the notes, so on page 87 to 80 in the notes, I've shown you the particular solution by variation of parameters. So we've seen two methods for particular solutions: undetermined coefficients and variation of parameters. Undetermined coefficients tells you what form the particular solutions have in these two cases. One day I've already used up most of my chalk. Let's buy more chalk. But in these two pages of notes, you can see both particular solutions worked out using of parameters. But for purpose of a homework problem, and you can use whichever method. Like if f of t is of a right form, you can use either undetermined coefficients or variation of parameters. I will emphasize there is one problem on test 2, motion of an object on a spring, but that is the simple way. So no external force and no damping. You just find the equation of motion, and you'll see that in the practice test. But the homework deals with all of these different scenarios, so I need to cover all of them for that. So, okay, so that's the end of the material for test 2. So what I will do during the next class period, so what I will record on Wednesday is I'm going to do a review session where I'm just going to go over the problems on the practice test. And then so here's what I will do for next Monday, so April 6th. I have that on the schedule as also a review. So after Wednesday's class, you go ahead and watch that, or try working out the practice test, or both. Send me your questions, and I'll get back to you individually, but if I have questions that appear to be of interest to the whole class, then I will address those questions in the video that I tape, that I record next Monday. If I don't get any, then there just won't be a video from that day, and there'll be no recording from Wednesday, April 8th either, because that's when you'll all be working on the test. So the next regular class where I actually cover things will not be until Monday, April 13th. 2 weeks from today. So, so see what you can do for practice test. Let me know if you have any difficulties, and I'll discuss it in my next video.